Welcome to section B of this paper, which is science paper 1, okay, 2021 GCE, section B, solutions. Question 1, we answer all the questions. Figure B 1.1 is a diagram showing a vernier calipers. What is the reading shown on the vernier caliper? This is in centimeters, but this is read in millimeters. Okay, if you convert it to centimeters, you have to be mindful. Therefore, main scale reading is 5.4 centimeters. Vernier scale is 0.02 because the degree of accuracy of the vernier caliper is 0.1 millimeters, but when this is converted to centimeters, it will have 2 decimal places. So my final reading is 5.42 centimeters. Okay, so how do you read this? You look at the last the focus is not happening here. You look at the last mark here before the 0 mark. This is our 0 mark. Okay, so you look at the last mark before the 0 mark. Okay, this is our last mark before the 0 mark. Do not look at the frame, but you look at the last mark just before the 0 mark, and then you consider that as the last part or the last point where you should do your reading. Okay, where you should do your reading. So this is how I came up with my 5.4, 0.1, 0.2, 0.3, 0.4. And again, you have to look at the way this scale is made. Anyway, that's our reading right there. Number B, convert the reading in meters. I divide by 100 because this is in centimeters. This gives me that, therefore 0.0542 meters. That's my reading in meters. I mean in meters. Write the reading in standard form. I've written it this way. Okay, I've not rounded up or down, but I'm just moving the decimal point. Therefore, I'm maintaining these values here. This is standard form. How many significant figures does a vernier caliper reading in meters have? 3. There are 3. Question B2. A man of mass 75 kgs on Earth goes to the moon where the gravitational field strength is 1.6. How did he go? What was his name? Okay, I think that doesn't matter. If things become tough, that's what you start asking. A, what is the mass of the man on the moon? Mass is constant, so it will remain at 75 kilograms. Number B, what is the weight of the man on the moon? Weight depends on G, or the gravitational force. So the weight is 75 times G, and the G there is 1.6, so it will be 120 newtons. Number C, a light truck of mass 2000 kilograms accelerates from rest at the rate of 1.5. Calculate the force required to accelerate the car at this rate. Therefore, you use this formula from Newton's third law of motion, which gives us 3000 newtons. 3000 newtons. We'll get to question. Okay, this is question B3. Diagram below. Diagram showing a uniform meter ruler freely suspended at its center. A Newton meter is hung 20 centimeters from the pivot, while 4 Newton weight is suspended 40 centimeters from the pivot. That's our diagram right there. The meter ruler is in equilibrium. Okay, state the principle of moments for a body in equilibrium. Therefore, the principle in short states that clockwise moments about the pivot are equal to anti-clockwise moments about the same pivot. For it to be in equilibrium, the sun is setting and it's actually passing through the window here in the savannas of central southern Africa. I think this should be my last video for today. I gotta go, but let me finish up this section first. B, calculate the reading on the Newton meter. I actually had seen it differently. I didn't see the aspect where the question says the ruler is balanced at its center here. Okay, so I had calculated it from the difficult point of view where I had gone very far, but I saw it, so I had to make corrections and redo it. So this is the moment brought about by the 4 Newton mass or weight, which is anti-clockwise, and then this is the moment brought about by the Newton scale, which is the clockwise one. So the value of F, or the reading on the Newton meter, will be this. Okay, will be 8, and that's that it will be 8. C, state the reason whether the Newton scale or Newton meter reading would increase or decrease when the 4 Newton weight is moved to a distance of 30 centimeters away from the pivot. The Newton meter reading will decrease because the counter moment caused by the 4 Newton weight will decrease. Therefore, the closer this weight moves to the center where the ruler is balanced, the lower the moment. Moments are greater when they are far away from the pivot. Therefore, you even use less force. So even the reading here will actually reduce. Okay, will reduce because the counter is becoming less. And then at some point, of course, if it becomes direct to this point here, then that would be another thing. But that's my thinking right there. Please correct me if I've gone off road. For question B4, a small hard ball has mass of 0.14 kgs of mass, of course, is thrown vertically upwards and reaches a height of 12 meters above the point from which it is thrown. Calculate the work done in lifting the stone to the height it attains. In this question, they're saying a hard ball, and then they're saying calculate the work done in lifting the stone. They should have just said the stone here. So work is equals to force times distance. The distance is the height. The work done, the force or the work done or the force on the ball is equal to its weight, because this is vertical elevation. So the force that is applied on the stone is equal to its weight. So I convert this to weight by multiplying by 10, because weight is equals to mg, so it gives me 1.4 newtons. So my final amount of work done is 16.4. This is equal to the energy done in lifting the stone. Okay. Number B, what is the velocity of the ball at maximum height? The velocity is 0, because each time an object is thrown vertically upwards, it has to come down, provided it does not reach the velocity or escaping velocity, speed of escape. It has to fall down. So before falling down, it has to momentarily stop and then turn back around. It cannot just bounce off. It has to momentarily stop. So the velocity has to be 0. But through calculations, you should take note to say the speed at which the ball is going to approach the ground is equal to the speed at which it was thrown up. Therefore, the velocity of the ball before hitting ground is 15.49 meters per second. I use this formula here of velocity final initial plus 2gh. G is acceleration. Since it's since it's gravity, I use g because g is a constant. So I simply replace this, and then this ball is going up, so my g becomes negative. Remember, our acceleration is only positive if an object is moving in the direction of the force. So since the ball was going up, it was actually slowing down, okay, because gravity was pulling down and the ball was going up. So that is the reason why it finally or eventually stopped, because at some point, gravity finally overcame the initial force the ball was pushed with. So my g becomes negative because the ball is going up. So my initial velocity is this. I'm looking for my final. Therefore, that's my initial velocity. 2 is a constant. G is negative 10 because the ball is going opposite to the force. Then this is my distance. Then when I work out this, my final velocity comes out as 0. Okay, root 0 is 0, so that's my 0 right there. See, on a windy day, the same stone is thrown upwards with the same energy, but force fails to reach the height reached earlier. Why does it happen like this? Okay, this is due to friction with air or air resistance, which caused the stone to lose energy. Friction causes loss of energy, okay, channeling of energy to other forms. So on a windy day, the stone may not reach the same height because of air resistance. Total marks are hours. My next question there reads, there's a displacement graph, okay, displacement distance graph in terms of waves, okay. Figure 5.14 shows a transverse wave, or shows transverse waves. Displacement against time, or against distance. Find the value of the number of waves in figure 5.1, B5.1. There are 5. Okay, how do you know the number of waves? You simply count the cycles. One cycle is made up of one crest and one trough. Therefore, this is a crest, that's a trough. So one cycle will start from here up to there. It's 1, 2, 3, 4, 5. There are 5 waves or 5 cycles or 5 wavelengths. 5 wavelengths, because wavelength is the distance of one cycle from that point to another. Period is the time taken to produce one complete cycle. Therefore, if this was the distance time, then we would learn it in that way. What is the amplitude of the waves generated in the figure above? Amplitude is the maximum displacement from the mean. Okay, so the maximum displacement from this is our mean, the x-axis is our mean, the maximum displacement is about 5 meters. So our amplitude is 5 meters, which is here. Calculate the speed of the waves above if the number of waves in figure B5.1 are produced in 2 seconds. The wave equation is right here. We have velocity is equals to frequency times wavelength. Velocity is what we're looking for. Frequency, we don't know. Wavelength is 1.2. Okay, I mean, yes, it's just like that. So let's first of all find, how did I find the 2.5 and this here 1.2? Frequency, first of all, frequency is equal to number of cycles over time, and the number of cycles is 5 as we counted. Okay, it's 5. Therefore, 5 over, we've been told that these waves are produced in 2 seconds. Therefore, in 2 seconds, like right there. So the frequency comes out as 2.5 Hz. 2.5 Hz. Then wavelength, when you look at our graph there, the total distance covered is simply 6 meters. Okay, there are 5 of them in 6 meters. So you simply divide 6 divided by 5 for you to know how these 5 waves are sharing the 6 meters. So you simply come to your wavelength. 5 over 6 gives you 1.2 meters. So you plug in these values and you have your 3 meters per second. 3 meters per second. That's your velocity of the wave. Question B6. Figure 6.1 shows light in air striking the vertical side of a rectangular glass block at an angle of incidence 60 degrees. Your rectangular glass block is right there. The refractive index of the glass is 1.6. So the incident ray is this, the angle of incidence is this one here, our angle of refraction is this. This is just another angle of incidence in the glass, okay, before having the emergent ray here. So what is refraction, refractive index? What is refractive index? Refractive index is usually denoted by the letter N. I would call it letter N. Is the ratio of the sine of the angle of incidence to the sine of the angle of refraction, which is constant for every substance. That would be the general definition of refractive index. The other way of defining it would be the degree to which a material refracts light, okay, which is constant for every material. Therefore, the degree to which light is bended between two media, okay, between two media. And this refractive index, refractive index is always calculated by taking light to always move from the less dense material to a more dense material. You should mark me right on that one. Every time you're calculating the refractive index, always take light to move from the less dense to the more dense. So even if light is moving from the glass to light, if you want to calculate for the refractive index, take it to be moving from from air to the glass. So your angle of incidence should always be in the media where the density is less. B1, calculate the angle of refraction, R, in that figure. Our formula is that sine I over sine R. Our refractive index was given as 1.6, therefore 1.6 right there. Sine 60, this is the angle of incidence as in the figure here. And so you do your algebra, make R as subject. So I do my cross multiplications here. Finally, I make R the subject. This is sine 60 over 1.6 over sine. Then I raise the sign to make it sine inverse. Then my angle R is 33 degrees. My angle R is 33 degrees. What is the critical angle of the glass block? Critical angle is the relationship between the critical angle and the refractive index is expressed in this here. The critical angle is simply the angle at which the angle of incidence at which the angle of refraction is 90 degrees. Okay, and this is only observed when light is moving from a dense material to a less dense material. So let me just say this is a formula here. We can learn about that one later. Sine 90 over sine C, which is our sine critical angle. Then sine C, I'm making C the subject. Finally, I have this. This is my refractive index. The critical angle is 39. The critical angle is simply the angle at which light trying to move out of a dense material like a block will be partly reflected out of the block and partly inside the block. Therefore, when the critical angle is reached like this angle of incidence within the glass, when this angle of incidence in the glass is equal to the critical angle, it's at a magnitude that we call critical, then this ray will not come out of glass and it will not go into the glass. It will be along the boundary, okay, such that the angle of refraction is 90 degrees. And this is always calculated like this. So this critical, or if they, okay, I think I'll explain better in the under the topic of light. When this angle is bigger, then total internal reflection occurs. But let's save that one for the next time, so that we don't really delay in solving this paper. We have scored all the 5 marks, by the way. Let's get to question 7. In question 7, explain what is meant by magnetic field, a region around the magnet in which the magnetic energy or force has effect. Electric field, region around an electric conductor carrying current in which electric energy has effect. Okay. B, complete the diagram in figure 7.1 B to show the pattern of the yeses that they're always drawn like this. Where they are crowded, it means the magnetic field is stronger. Where they are spaced, it's much weaker, and they're always drawn to emanate from the North Pole and end up in the South Pole. Therefore, there are always these lines which are directed from the north to the south. That's a bar magnet. That's a magnetic field for a bar magnet. C shows a positive charged sphere as placed near to an initially uncharged isolated conductor AB. Okay, complete the diagram to show the charges induced in the diagram. Okay, so it's me who did this. Okay, if this is positive, then it's going to attract electrons in this substance, okay, in this substance, and then since the electrons are going to shift to this side, the other end will be relatively positive. That would be the induced charge here. Remember, unlike charges attract, like charges repel. It's just the same as magnetism. We have scored 5 solid marks. We turn over. B 8.1 shows an electric circuit containing 2 resistors. Question A. On the figure, draw a circuit to show how a voltmeter will be used to measure the potential difference across the 6 ohm. It's always drawn in parallel to the circuit, okay? While the ammeter is always drawn in series to the power source. This one is always connected across, okay? Across the device whose speed is being measured. This one is always connected in series with the power source to count or measure the current in the circuit. Number B. When the switch S is closed, calculate the current through the ammeter. So current through the ammeter, since the ammeter is connected in series to the power source, the current is going to be the current for the whole circuit. So the power source has got a voltage of 16, and then we have to find the effective resistance. These resistors are in series, so you just add them. Okay, just add them. This is 8, so you add them to give you 8. 16 over 8 from voltage over resistance. The current is 2. The current across this is the current across this. Therefore, the current across all of these, including the battery, is 2 amps. 2 amps. C, what is the potential difference across the 16 ohm resistor? Voltage is equals to IR, current times resistance. The resistance is there. Current, you already know, it's 12 volts. Voltage is not the same in series, but current is the same. So if this is 12 volts, then 16 minus 12 is what? Should be 4, right? Yeah, 16 minus 12 should be 4. It means the voltage across the other resistor is 4. They are sharing the voltage because they are in series. Therefore, voltage in series is not the same across components, but current is the same, and voltage in parallel is the same across the components in the parallel section, but current is not the same. We move on to the next question. Okay, so this is our last question in section B before we go to section C. B9, uranium-238 decays to form a nucleus of thorium by emission of an alpha particle. Thorium has a symbol of 234-90Th. That's a nuclide. These are nuclides of these elements as they are, just like in the periodic table. Although most radioactive elements on the periodic table, the ones that are extremely radioactive, do not have specific masses. Okay. They are never really given specific masses. What is the meaning of the nucleon number? That is the atomic mass number. Nucleons are protons and neutrons. So they are found in the nucleus. So the nucleon number is their total number. Number B, write a decay equation to show how uranium-238 decays to thorium after emitting an alpha particle. So that's my equation right there. This alpha, sometimes it may be there, it may not be there, but this just shows that the decay just involves a single alpha decay. It can also be a double alpha. Okay, you have to know what an alpha particle is. An alpha particle sometimes is called a helium nuclei. They are sometimes called helium nuclei. Therefore, they may be given this symbol. They are mostly given this symbol. But alpha, that's the symbol for alpha, but you can also use that one. So an alpha particle has a mass of 4, therefore it has got 2 neutrons and 2 protons. So in the mass, you subtract 4 because the parent nucleus loses mass by 4. And in that 4, you have 2 protons and 2 neutrons. That's why the helium nuclei or alpha particle has got this symbol here. So thorium is going to it's going to have a mass that is less by 4, and then atomic number less by 2. 92 goes to 90, then 38 minus 4 goes to 34. So this is the 4 that you subtract from there. That's the 2 subtract from there. Thorium-234 decays to an isotope of protactinium, Pa, by beta decay. Write the decay equation to show this process. This is a thorium. Single beta decay, it can be a double beta decay, even a triple beta decay. A beta particle, I would say, is a negatively charged particle, which is, I would say, equivalent or equal to an electron. That is why sometimes it may be given the symbol of an electron right there. It may even have this negative charge right there. And then for the alpha particle, an alpha particle has a charge of +2. Okay, this is a charge of +2, this is a charge of -1. So it may have this beta symbol or the electron symbol, whichever one can be used here. The mass is negligible, therefore the mass, there is no mass, just put zeros there. Single beta decay, this is how it would go about. Remember, a beta decay involves the breakdown of a neutron to form a proton and an electron, or a beta particle. Let me just call it a beta particle. Therefore, a neutron is converted to a proton, and a beta particle is emitted. So the number of protons will increase by 1 here, because 1 neutron has decayed to produce 1 proton and a beta particle. So this will go to 91, and because protons are still part of the nucleons, the mass will not change. So the mass remains 234, but the proton number or atomic number goes to 91, protactinium. This marks the end of our section B. Hope it was helpful. Have a good day until we meet again. Bye bye for now, and remember to subscribe and share this link. Bye bye for now.